link matrix, and this is the weighted average, 1 minus t and t, a weighted average of A and S. Okay? T is a tunable parameter that goes between 0 and 1. Okay? If you take t equals 0 here, then the matrix capital M is just capital A, and you have the original problem. If you slide t all the way up to 1, well then M is S, and you've blown away your actual web structure, and now you're just giving everybody the same, you'll give everybody the same importance score. Okay, we'll use M instead of A. Here's what you could prove. If t is bigger than 0, then you can prove that M has a unique eigenvector with eigenvalue 1. There will not be 2 independent eigenvectors or R independent eigenvectors. There will be one and only one eigenvector up to scaling that has eigenvalue 1. The eigenvector will have non-negative, it'll actually have positive components. And the power method, when you implement it, as I showed it to you, will converge to this eigenvector. And in fact, how fast will it converge? It depends on t. The bigger you take t, meaning the closer you get it to 1, the faster the power method will converge, but the price you'll pay is the bigger you take t, the more you've distorted the original problem into an egalitarian web. Okay, so, but this eigenvector you compute is what you use for the importance ratings. Google reputedly used, or uses, 0.15 for t. So they take 85% of the original problem and blend in 15% egalitarianism. And the result is that you solve this problem of not having a unique eigenvector. Now you have a unique eigenvector, and the power method will converge to it. And it turns out it converges geometrically at a rate of 0.85 to the k if you measure it appropriately. 0.85 being 1 minus t. Okay? If you take t to be too close to 0, the power method will still converge, but very slowly. And if you take t to 1, the power method will converge in one iteration, but you'll just rank everybody to give you the same importance. Okay? But now, here's the one last little twist I want to show you in this talk. How can you use the power method if you have to deal with a 10 billion by 10 billion matrix? Because 10 billion is 10 to the 10th. So a 10 billion by 10 billion matrix, you need 10 to the 20th entries just to store the matrix. So of course, it's natural to ask 10 to the 20th. What if I could store every entry in the matrix with one lousy byte? Is 10 to the 20th bytes a lot of information? Well, go to Walmart and buy a terabyte drive. That's 10 to the 12 bytes. So you need 100 million terabyte drives to store the matrix. That's still too many drives, I would say. Okay. I don't think storing these matrices naively is going to cut it. But here's what fixes the problem. Okay? Sparsity. In our original web of 4, or in any web really, notice that the matrix A has a lot of zeros in it. In fact, it only has non-zero entries when the page corresponding to one of the columns links to the page corresponding to one of the rows. Okay? So if the column I, row J position is non-zero only when page J links to page I. Well, if you think about the web, 10 billion pages, okay, but most pages don't have 10 billion links going out. They have 10 links, 20 links, I don't know, whatever. You can expect that most of the columns in this matrix will only have 10 or 20 or 100 non-zero entries. You don't have to store the whole matrix. Only store the non-zero entries and their relevant rows and columns. So if I were going to store a matrix like this, I'd say, okay, in row 1, column 3, there's a 1. In row 1, column 4, there's a 1/2. And I do that all, and most of the row column positions I don't have to deal with because they're 0. I don't list them. Okay? Most entries in A will be 0. So this means two things. First of all, A can be stored much more efficiently. Even if A had 10 billion rows and 10 billion columns, but only 100 entries per column on average, then you have to store 10 billion times 100 entries. That's 10 to the 12th. That's a terabyte. That's not bad. Okay? You could store A in relatively little storage. Also, so you could store it in 10 to the, I said 100 non-zero entries per column. If it's even 10, then you can store it in even 100 billion bytes, 100 gigabytes. It turns out, if you're smart about it, the fact that the matrix A is mostly zeros means that you can take A times X. You could do A times X relatively quickly. If you actually gave me a 10 billion by 10 billion matrix and said, take this 10 billion dimensional vector and multiply it by A, even if I could store A, even if storage was infinite, that would still be a lot of computation because A times X would also take about 10 to the 20th operations, floating point operations, and that's a lot. But if A is mostly zeros, most of the work is irrelevant. You don't need to take 0 times 2.6 to figure out the result is 0. There's no point in doing that computation. You can do A times X very quickly. And you can easily check, this is a little exercise you can try later. If you give me a matrix S that is all 1 over n, all entries are 1 over n, where n is the number of pages in the web, then it turns out S times X is a vector where all the entries are 1 over n as well. As long as, if we agree to scale our eigenvectors so the components sum to 1, S times X isn't a quantity you even have to compute. You just end up with a vector that has all 1 over n's as its component. So there's no work to do in computing S times X. So the upshot is, the core of the PageRank computation, this iterative process where I repeatedly replace a vector with m times the vector and do that over and over and over again, I compute A times X efficiently using the fact that A is sparse, mostly zeros. W equals S times V, that's the vector with all entries 1 over n, and then M times X is simply this linear combination of V and W, so it's super easy to compute. Well, if you have 10 billion by 10 billion matrix, it's still some work, but for the computer, it's at least trackable. And you just repeat that process to converge it. This is the original PageRank algorithm that Google implemented. So that's the guts of the PageRank algorithm. It turns out this Google approach to importance ranking, it's been applied to a lot of different types of webs where you have interconnectedness, where, for example, in food webs, somebody sent me a paper where you have a bunch of species that prey on each other, and a link from one species to another means that species eats the other species, and you want to know which are the most important species to this food chain. And you're more important if more people eat you, because if you were like removed from the food chain, it's more like it disrupt the web. Okay, well, so that's one place I saw it applied. I've seen people, you know, I wrote a paper on this about 10 years ago, and suddenly people send me papers galore on where they've applied the PageRank algorithm. Game theory, medicine, I don't know, I've got like a stack of them on my desk. Okay, of course it's been applied to rank how important mathematicians are by citations. You link from one mathematician links A, links to mathematician B, if mathematician A cites B in a paper, and so you can cite who's most important. Okay, and here's the part that I'm more and more surprised as I get older and older. When I took linear algebra as an undergrad, man, it was like the driest, most desiccated subject I'd ever seen in my life. It was just so boring. It was just like, I mean, the computation was Gaussian elimination, or if you took the abstract version of it, it was modules over rings, and writing down matrices was considered to be in poor taste. But it was just like, mind-numbingly dull. But you know what? In fact, it's the core of so much modern scientific computing. It comes up everywhere, and it's still a super vibrant subject. I've been working in this area called compressed sensing recently that's basically applied linear algebra in some form, where you might think there's nothing else to say about solving linear systems of equations, but there's lots to say about it. So that's another important takeaway message. And of course, the most important takeaway message is if you pay attention to your math professors, you might also become billionaires like Google's founders. Thanks.